Building artificial general intelligence currently requires massive scale. We picture football fields of server racks generating blistering heat, powered by specialized processors like this NVIDIA GH100. This is the hardware currently accepted as the only way to process high-level AI models. But the energy needed to drive this infrastructure is placing an unsustainable strain on global electrical grids. We are reaching a physical limit on how much power we can generate just to keep these processors cool and fed with data. Yet, there is a documented anomaly in the research. A modern 2 billion parameter AI model was recently observed running inference with a 10 to 20-fold energy advantage over current standards. Most surprisingly, it was running on this, a CPU from 2007. This Dell laptop built for Windows Vista executed a modern AI model without the help of a single GPU or floating point unit. Successfully running modern intelligence on hardware from nearly 20 years ago suggests that the specialized infrastructure we see today might not be the only path to AGI. In a standard processor, AI computation relies on floating point matrix multiplication. To perform these millions of operations, the system constantly shuttles data from memory. This von Neumann bottleneck creates friction, consuming a massive amount of power. As models grow in size, this physical transfer of data scales exponentially. Eventually, the system spends more energy moving information than actually processing it. The overhead of this floating point math architecture is the primary barrier to energy-efficient AI. Researchers are now testing an alternative called the Basin Quotient State Machine, or BQSM. It's a computational model built on a different logic than either classical or quantum systems. The BQSM uses a Kuramoto oscillator ring. Instead of processing binary bits, it hosts multiple, independent signals that oscillate simultaneously within a closed loop. These signals interact through continuous physical interference, a process called mode coupling. Rather than solving digital equations, the signals blend and influence one another. The system calculates by naturally settling into a stable, locked shape, known as an attractor basin. Once the waves lock, the calculation is complete. The hardware isn't performing math. The continuous dynamics of physics are settling into a result. For a digital chip from 2007 to run this model, it has to be able to read those continuous analog results. The BQSM uses a 4-state encoding method, compressing those physical ring states into a 2-bit digital format. This compressed data can be executed by a specific older instruction set found on early Intel chips, called push-shuf-b SIMD. By using this instruction, the processor bypasses complex math equations entirely. It simply performs a direct integer table lookup to find the pre-calculated physical state. The 2007 chip is fast and efficient because it reads pre-calculated physical outcomes, skipping the energy-intensive floating point arithmetic. The 2007 test proves we can approach the absolute limits of energy efficiency, a boundary in physics known as the Landauer bound. Removing the von Neumann bottleneck changes the physical footprint of intelligence. We move from energy-draining data transfer toward a more frictionless, continuous flow of information. This suggests a future where high-level intelligence operates on low-power, everyday devices, rather than being restricted to massive centralized server farms. Scaling to general intelligence likely depends on a shift in computational architecture, rather than the continued expansion of current hardware. AGI may ultimately rely on orchestrating physics directly, rather than simulating it through layers of standard digital logic.